So if you were at the Hack House in Istanbul during the event last November, you might have seen Martin give this speech, but if not, it'll be pretty similar, just way less German. I'm Megan Fitzgerald. I work as a developer relations engineer at Avalanche. I've been here about a year now, and today I'm going to talk about the basic structure of Avalanche and then examples why our cross-subnet communication protocol is so incredible and will really change the game for blockchains. Just a show of hands, how many people in here know what a subnet is? Okay, it's a good majority. So the way that we think about blockchains at Avalanche, just to I'll speed through this since everybody similarly knows this, but we kind of think about blockchain performance as a measure of time to finality and throughput. So every single chain can be thought of as like a highway. And on a highway, you have your entry point, your ending point. The ending point we'll think of as when a transaction is finalized, when a block is included and finalized as part of the network. And the transactions are cars being sent from their source place, I guess, the RPC endpoint that you submit them on, to the chain itself and forever persisted in the state, right? So there are multiple blockchains, obviously, that people here are probably very familiar with. And a lot of these chains are, or majority of these chains are monolithic. So networks like Ethereum, networks like Bitcoin, even networks like Sui and Aptos are monolithic chain environments and only include one blockchain where every Zap developer who creates an application on these chains has to share the block space with the chain. Bitcoin, we know, has a really, really long time to finality. I don't remember what it is today, but as the network grows, the time to finality gets longer because of proof of work and things like this. Ethereum's is a little bit shorter, a little bit wider than Bitcoin. Obviously, you can have composability more so on Ethereum than you can on Bitcoin. But again, because of the consensus mechanism that Ethereum employs, time to finality can be anywhere from 20 to 40 minutes and will grow as the network grows as well. Avalanche consensus is extremely fast. On our primary network, transactions are normally finalized in less than 2 seconds, sometimes less than 1. And Avalanche is actually very incredible because we run a multi-chain network. So the primary network that everybody gets very confused about has 3 different chains running on a subnet. This subnet is validated by every validator in our network at the moment in time. And these 3 chains serve specific purposes. And the initial thought process behind this was that we wanted chains that did specific things so that those specific things would not suffer by all of them trying to be performed on the same chain. When you try to put a ton of compute into one machine, that machine eventually will get spread thin. Things will start to become expensive. Developers and dApps have to compete for block space, and that just is what drives transaction price up, but also what drives the state of your network to become kind of unmanageable because the validators obviously have to sync all that historical data. All the validators in our network have the ability to sync as many or as few subnets as they want. Right now, it is a requirement that they have to validate the primary network. But you end up with this massive combined throughput of subnets, like a ton of highways, because each subnet runs its own copy of, at this point, the Ethereum virtual machine. But we are a VM agnostic system. So any of these subnets could run a VM similar to that of Solana or Move or whatever virtual machine you and your developers would like to build your application on. You can spin up a subnet, run that chain, own your block space, and share it with nobody. So it's a very, very powerful mechanism. And then obviously this results in every single time a new subnet is spun up, the effective throughput of our whole network is increased. So if you want Ethereum, what's the max gas per block? I don't even know if I know that. I think Ethereum processes 1 billion units of gas per 30 million per day? Per block. 30 million per month. 30 million per block. In our network, if we only had 2 subnets, that would be 60. We have about 100 subnets. So just times that number by 100. That's how much gas you can have throughput. And none of the other subnets get any reduction in performance because if your validator isn't validating that subnet, then it's like it doesn't even exist to them. But what ends up happening is the fragmentation of networks, right? if you have different blockchains, obviously everybody knows what a pain it is to bridge from network to network. Avalanche's structure, though, accounts for this because we know that if we were to fragment every single network and make it so that they couldn't communicate with each other whatsoever, it would effectively be like every application has to build their blockchain from scratch and build their user pool from scratch, build their liquidity from scratch. And that's like, obviously no one seeks to reap any benefits that way, right? We still benefit from interoperability. So the way that Avalanche works is we have a very simple infrastructure for doing cross-subnet communications based on the way that networks are spun up here. So today I'm going to be talking about AWM, but I'm also going to be talking about what makes this possible for our network. So a message, when sent from one chain to another chain, in order to be valid on both, has to include proof that the event actually occurred. It has to be, let me see if I can get to the security. It has to be authentic. You have to be able to trust that that message is what it says it is, and that it wasn't messed with from the time it left the source network to the time it was delivered on the destination network. It needs to be non-repudiable. I think that's a word. It has to, basically, once it's sent, you can't take it back. Because if you could take it back, then you could have, a lot of issues with that. You could say that you own an asset double the amount of times that you do, or you can send somebody something, and then if you were able to take it back, then effectively you could scam somebody into thinking they own something. And then integrity of the message is really important because what you don't want to end up happening is someone in the middle getting involved, changing what that message says, and then, affecting the network in a negative way because they wanted to attack you or something like that. Cross-chain interoperability has many use cases. Obviously, there's very simple use cases like asset bridging. There's DAO voting across chains. Cross-chain liquidity pools is one that we see a huge opportunity for. It's something that Chainlink does with Chainlink CCIP. That's extra network. Right now I'm talking about within the Avalanche network. So every message sent from source subnet to destination subnet is insured. Its authenticity is insured, its non-repudiation is insured, and its integrity is insured by Avalanche warp messaging. And the way that this happens is that we take a message sent from subnet, like a source subnet, and we wrap it in a signature. These signatures are produced by something called BLS cryptography. We at Avalanche did not invent this. It was some really, really talented researchers at Stanford who invented, or not invented, but discovered BLS signature schemes and wrote a paper on it. But these schemes include 3 functions. So the first thing is you can generate a key from some cryptographic curve. It's the same way that you generate public and private keys on Ethereum networks or EVMs, but the way that it's produced is not exactly the same. So they have a different encoding. Then you can take a message and then the secret key and sign that message to produce a signature. This signature effectively is able to be undone by the verify function. So if you have the signature, the message, and then the public key of the key that created that signature, you can produce a Boolean to prove whether or not that is true or false. So the way this ends up being extremely powerful because what you can do is you can take these keys and you can, I'm not explaining this the way I want to explain it. You can, as a source or a destination subnet, basically receive a message from another chain. You can go to the P chain on the primary network, look up all the BLS keys of those validators of that source chain, and with their public key, verify that the message that they gave you, along with the signature that it's wrapped in, was true and hasn't been tampered with upon receipt. And yeah, I think it's just incredibly powerful. You can also have these multi-signature schemes based on any level of security you want. So you can toggle that from a minimum of like 10% of the network all the way up until 99% of the network if that is a requirement of security that your source subnet has. Something I do want to talk about that is kind of at the end of this, I believe, is why is this valuable and why is this more valuable than trusting something like a third-party bridge? This is more valuable than trusting a third-party bridge because you don't have to trust like a separate third party between you and the party that you want to interact with. You just have to trust the security of the Avalanche network. Since the whole network is already validating the P chain, you know via that the message hasn't been tampered with, and the public keys that you are using to decode that message that you've received are valid. I think I'm doing this out of order though. Load and trust. Yeah, so this very famous quote, cross-chain communication is impossible without a trusted third party, contrary to common beliefs in the blockchain community. Yeah, so like this is where protocols like layer 0 come into place. It's the reason why we kind of need these external companies to do cross-chain communications, because you essentially trust their protocol that you won't have the duplication of assets, you won't have repudiation happening where someone sent a message that they didn't mean to send. Within the Avalanche network and between subnets, you're just trusting what you already trust. You trust the P chain, which is globally validated by every validator in our network, and you trust the validator set of the subnet where the message originated. Is there any questions about that? Okay, let's go back to our demonstration then. So let's see. So I showed you guys this earlier, the 3 signature schemes that are enabled by BLS cryptography. These can be enabled by multi-signature schemes. Again, like it's the way that you verify that the message that you receive is valid by using publicly available information, those public keys that are posted to the P chain. What ends up happening though is if you want to send a short message like hello or hi, I'm here, let's say it's like 64 bytes. One signature is 48 bytes. If you want to wrap that with just one signature from one validator, that would be 48 bytes. But if you're communicating with a network that has 1,000 validators, unless you have a way to aggregate that, 1,000 signatures would result in a signature of 48,000 bytes, which is extremely large and very unwieldy. But the way that BLS key cryptography works is that it can aggregate all these signatures, so every single validator signs that message, and then those messages are encrypted into one signature, which would only be 48 bytes. And all of this aggregation happens with relayers that lie between your networks, and it's done completely off-chain, so it doesn't affect your blockchain's performance whatsoever. Again, you take all the signatures from every validator on the source subnet, you sign the message, and then you take those signatures and you aggregate them into one. And then you can verify that not by having to go to the P chain and look up every single public key, but by taking the aggregated public key of all the validators in your source subnet and de-encrypting that with the same functions we saw here. It's extremely powerful. So this is a lot of cryptography. And whatchamacallit? Solidity developers don't tend to touch this stuff. dApp developers just deal with their contracts on their chain. The good news is that we've taken this is boiled down into AWM. We've created the teleported protocol, and the only thing you'll have to do is interface with a couple of predefined interfaces that have been deployed onto our primary network and are very easily deployable onto any subnet that decides to spin up. AWM is what I just explained. This is just a better, I think, visualization for it. So every single time a subnet is deployed on Avalanche, the validators that are validating that subnet, when they come online, they have to register their public key, the BLS public key, to the P chain. So again, this is state that is stored in the primary network. It's not stored on your own subnet. And then it also validates the stake weight because, I mean, if anybody knows proof of stake network, when you validate things, it's not like every validator is weighted the same. It's just like you kind of take a conglomeration of all the networks, or all the stake weights in the network. And then your subnet also has a BLS key that is registered when it is created. But it's like the node ID, the public key, and the stake. So the relayer, what it does is it will look at the P chain when it receives a message from the source subnet, It'll go to the P chain, it'll look up all those BLS keys, it'll take the individual signatures and the unsigned message, and it'll validate it using that verify function that BLS cryptography enables. So you get the message with the aggregated signature, and then on the destination subnet, the destination chain's validators receive the message submitted as a transaction on that chain by the relayer. It takes the aggregated signature and it verifies it. It confirms that the message that was meant to be received is in fact the message that was sent, and then it'll submit it as a transaction on the destination chain. It's extremely important to emphasize how lightweight this protocol is. Teleporter makes it so that Solidity developers, instead of having to deal with every aspect that I just described, they only have to deal with the interfaces that are a one-time deployable, and then their dApp would be programmed as any other Solidity dApp that is already programmed. It would use the teleporter's interface and a teleporter registry, which I won't get into today, to define how and when and why and what to do with messages sent from their chain to another or messages received. So it's very simple. So this is just a quick look at the teleporter messenger send function. So there's in the interface, we have this send cross-chain message. The input is just the destination chain ID. Again, public information, easily available on the primary network, and any block explorer can show you that. The destination address, the address of that you wish to send this message to. It could be somebody else's public address or a smart contract address. The fee info is a way for you to incentivize relayers in like a decentralized manner to deliver your message. And then if you are a privacy focused subnet and you don't want any relayer to send anything at any time, you can also specify specific relayers that you are trusting to deliver the message if you don't want to just leave it up for the open market to take it. And then you use a very familiar function with any Solidity developer, abi.encode, to take that message, encode it, so that it can be decoded on a destination EVM. This is the receiver interface. The receiver interface takes 3 parameters. It takes the origin chain ID, so the ID of your chain, of your subnet, the address that the message was sent from, the message that it received from the relayer, and it decodes it, and then verifies it. The validators verify it. So this is basically just a demo of what I've done. Cross-Subnet dApp. Yeah, this is, again, something we don't really need to go into. Teleporter messaging. So yeah, like I said, in order for us to deliver the message, we first need to take the message, in this case, test. We need to take the message type so that the destination chain understands how to decode it. We encode it with abi.encode. Bytes are sent to the destination chain along with the string that was the message and the type that the message was encoded in. And the destination chain will decode that, and the validators of that subnet will verify that that message is what it is. It has not been messed with, and whether or not it is just an arbitrary message or if it is a smart contract call, like a call for one of the functions there. Let's see. Yeah, so again, it could be some function. It could just be an arbitrary message. But this is basically just a diagram of what I just explained. So the majority of what I've explained so far is enabled just natively on Avalanche by any validator or any node that you run. The reason why we build Teleporter is because most of our subnets are EVM at this moment in time, and we wanted to create that encode and decode interface for EVMs that are communicating with each other. So you can, again, incentivize a relayer to send it if you want to just let it open for the open relayer community to take and to send. Or you can specifically verify, or you could specifically decide which relayer will send your message for you. The fee flow we won't have to get into. Load and trust. So the load considerations, source subnet is going to need to sign every message that is sent. This is done so after a transaction has been sent, and it is very lightweight, so it doesn't really cause any bottlenecks, and it is DOS protected because it's the same reason. It's the same reasoning as when you send a message or send a transaction to any chain. You're not going to send a bunch of messages that you don't want to send because gas is expensive and costs something. So you're going to be disincentivized from any kind of DOSing. And if you're running a permissionless subnet, people aren't going to be able to do that because they don't own an infinite amount of money. That's basically that. The relayer does all the heavy lifting. It does the signature aggregation, and it sends a transaction on the destination subnet. It is also the mechanism that does all of the double checking of the P chain and what the current registry of your validators are. So none of the actual verification is done by the validators of your source subnet, so you don't have to worry about that. The destination subnet does an aggregated signature verification. Again, it doesn't need to create every signature from scratch. It just needs to check that the aggregated signature and the message is valid, which is like one function call. And there's no load on the primary network because all that's being done is the P chain is being read, nothing else. And I already went over this, but again, the trust assumptions are, the trusted third party is the entire network, which currently is nearly 2,000 validators, and the source subnet validator set. If you didn't want to receive a message from another subnet, then you wouldn't validate it at all, and you wouldn't even consider it. So you don't have to worry about, about that happening. Okay, this is my information. I'm open to any questions and any feedback, and yeah. If anything is unclear or you guys want another explanation, I'm also happy to go through that as well.
Any questions? Seems it's all clear.
It's all clear?
All clear.
Oh, that's giving me too much credit. This is all my socials and the Avalanche developer toolkit that I have linked actually in that QR code. You can check it out. Feel free to ask me any questions after the fact. And yeah, I'm around to help. Thank you.